Okay, so now we'll be dealing with vacuum, we'll be looking at dual symmetry. We'll be revisiting it now that we have sources, but before we begin, here's the fix that I promised for the last section. Okay, cool. The fix for the last section was where we were talking about complex charge, where we have magnetic charge. So there's a phase factor that basically splits this charge up into an electric component and an amagnetic component, QE, QM. So this creates a magnetic charge or an electromagnetic complex charge current, J, which is you have the I keep thinking not thinking of a good name for this. The relativistic velocity W times this Q here, which is just going to give QEW plus QMWI. That's what this will end up being here. Which, if you want to relate it back to the original stuff, so this is plus JMI, where before we talked about complex, we had this thing up here, the source. So you can see that this is the source. It's the same thing. Well, the definition of the force before is when we had F dot what's it called? We had WQ, or we had EW. Like this was the force that we were dealing with up here. So if we consider just charge momentum with only electric charge, this is what the force would have been. But there's a motivation here that this is equal to the dot product between a bivector and a vector is the same thing as taking the product between a bivector and a vector and then projecting it onto the first grade components, because we need a vector returned for this. So the motivation here is then that you can then get rid of this dot product and only express the product in terms of this projection onto the grade 1. So what's done is multiplying by the charge current, the entire J, and then just projecting it onto this vector, onto its grade 1 components. And when you expand this, it actually ends up looking like F dot JE plus F wedge J M I. You end up getting this. And then if you continue expanding it out, I'm not going to do every little step just because the steps follow pretty much this. So expanding this out, you'll see that it will give a more complete version of the Lorentz force law, such that this Lorentz force law has magnetic charges as well. Even though, again, magnetic charges there's no proof they exist. So the more complete form of this would look like this. Plus QM So you just have contributions from the magnetic charge here and here. So it's just a more encapsulating formula. Okay, now let's move on to dual symmetry. So recall what vacuum dual symmetry was. Vacuum dual symmetry was when you had F, which was equal to F times some factor, phase factor. So even if you mapped F to a different phase, you would have it still be equal to 0, the gradient of it still be equal to 0. So this would be the symmetry. Directly inserting sources breaks this symmetry. Because if you have F equal to J, then when you go to the next one, e to the theta I, this is not true, that these are equal. But in all truth, this is actually a misapplication of phase transformations to J. So it's not actually that there is no dual symmetry for sources, it's that mapping like this does not give the same result. It's just a misapplication. If you're going to change F, you're going to have to change J as well. So instead, it's best to use e negative 1/2 theta I. To use this and a potential. And the mapping that you need to use is Z goes to CZ, C star, and J goes to CJ, C star. So therefore, because of the definition of using a gradient or using a potential, you end up with this Laplacian. Which is the same as doing this. Then you have C star, C star, because this C anti-commutes with this Z, so there's a star that ends up being there. Which is just the same thing as having E theta I equal to J E theta I, and this, of course, just implies that the gradient of F E theta I equals J E theta I. So you see that when you apply this transformation here, these two transformations, you end up with the dual symmetry being applied to both sides. And this is the correct way to actually do it. And so you see that the duality is captured by these mappings. Therefore, the duality is captured by, we have these, and F maps to F C star C star. So we have these mappings that therefore define the dual symmetry. And note that this actually leads to the Lorentz force being invariant. Therefore, the Lorentz force is invariant under dual symmetry. Now let's give a proof for this. The Lorentz force, again, is just given by F j times 1, so is equal to gradient of z times j 1, and this maps to, when you apply dual transformation, gradient of c, z, and then j, or c star, and then c, j, c star, 1, which you can anticommute these to each side, so you end up with gradient of z being equal to e to the theta I, then you have an e to the minus theta I j, which is just equal to gradient of z j 1 equal to f j 1, which is just the momentum again. So this is the result, that when you apply this dual transformation to the Lorentz force law, it also is invariant. So we can see that this is actually the correct way to perform this transformation.